Assalamualaikum. I am Rasha from Group Manjaro. I will explain the network configuration for our project. Our group design and configure a private virtual network using Oracle VM VirtualBox. The network consists of Linux server and a Linux client connected to an internet network. First, we configured the server hostname using the hostname CTL command and verified that the hostname was updated successfully. Next, we configured the IP addresses. The Linux server used a static IP address which is 192.168.1.254, while the Linux client received its IP address automatically through DHCP. The difference between a static IP address and a dynamic IP address is that a static IP is manually configured and remain fixed, where a dynamic IP is automatically assigned by a DHCP server and may change over time. To verify the network configuration, we perform connectivity tests using commands used such as ping, traceroute, and host. These tests confirm that communication between devices was working properly. Finally, we verified that the Linux server could access the internet through its external network interface. The successful result confirmed that the network topology was configured correctly and ready for the implementation of DHCP, SFTP, web server, and database. First, we run the command ls/sys/class/net to identify the exact name of the active network interface available on our Debian machine. As shown on the screen, our primary interface card is named ENP0S3. Next, we execute IP address, show the view the overall IP address assignment and the current operation status of all network links. To filter out unrelated network details, we isolate the output by running IP address, show ENP0S3. This allows us to focus strictly on the configuration metric of our primary interface. Next, we test the network deactivation. We execute the chain command sudo ip link set dev enp0s3 down to shut down the connection, followed by an immediate status check to verify that the state has successfully changed to down. To bring it back online, we use sudo ip link set dev emp0s3 up, which successfully shift the operational status of emp0s3 back to up. Then, we inspect the kernel routing table using the IP root command. This ensures that the data packet intended for external network are correctly mapped to our gateway pathway. Next, execute a localized network stability test using ping www.utem.edu.my. This send continuous ICMP request to ensure that our server has external connectivity with zero packet loss. To trace the hop path, synchronize our package index and install the traceroute dependency by running sudo apt update sudo apt install traceroute -1. Once installed, execute traceroute www.google.com to map out the explicit hop-by-hop path that our data packet traverses across intermediate router to reach the destination domain. For identifier management, we instantly change the machine identification to OS class using the standard system control architecture via sudo hostname CTL set-hostname OS class. To make this permanent, we manually edit the /etc/hostname file using the nano editor and execute the initialization script /etc/init.d/hostname.sh to inject the new identity into the system memory without needing a reboot. Now, let's shift our focus to IP management. Here, we access the /etc/network/interface configuration file to revert the profile from manual assignment back to dynamic management using iFace EMP0S3 init DHCP. To apply this change, we cycle the interface link state and fully restart the networking subsystem using sudo systemctl restart networking. This forces Debian to parse the update file and broadcast a DHCP request for a dynamic IP from VirtualBox. Next, this is the most critical setup for our enterprise server environment. We transition to a permanent static IP address assignment by modifying the interface file again. The profile is set to init static and we assign our fixed host IP address as 192.168.1.10, pointing it directly to our core gateway address which is 192.168.1.254. Finally, we cycle the link and restart the networking service one last time. This forces the system to stop requesting dynamic addresses and permanently bind our tailored static network parameters directly to our server hardware
network interfaces and static IP configuration. First, I check the available network interfaces on the Debian server using the command IBA. This allows me to identify the interfaces used in the system. I selected EMB0S8 as the internal network interfaces. Then, I edited the network configuration file /etc/network/interfaces. and assign the static IP address 192.168.1.254 with the subnet mask 255.255.255.0. After saving the configuration, I verified the setting using the IPA command and confirmed that the static IP address was assigned successfully. And then DHCP server configuration. After configuring the server IP address, I installed and configured the ISC DHCP server package. Then I edited the DHCP configuration file /etc/DHCP/DHCPD.conf. Inside the file, I defined the subnet network as 192.168.1.0 and configured the IP address range from 192.168.110 to 192.168.1.100. I also configured the default gateway as 192.168.1.254, which is the server IP address. This setting allows client to receive IP address automatically from the DHCP server. And after that, we have the DHCP validation and service verification. After completing the configuration, I validated the DHCP configuration file using the command dhcpd-t-cv /etc/DHCP /dhcpd.conf. The validation completed successfully without any errors. Next, I restarted the DHCP service using systemctl restart isc-dhcp-server. Then I checked the service status using systemctl status isc-dhcp-server. The output showed active running, confirming that the DHCP service was running correctly and ready to assign IP address to client. After the DHCP service verification, we have the clean testing and connectivity verification. Next, I moved to the Linux client machine and checked the network configuration using the command IPA. The client automatically received the IP address 192.168.1.10 from the DHCP server. This confirmed that the DHCP server was assigning IP address successfully. Finally, I tested the network connection using the command ping 192.168.1.254. The ping test was successfully with 0% of packet loss, confirming proper communication between the DHCP client and the DHCP server.
Begin by executing sudo apt update. This synchronizes our package index file with the Debian repositories, ensuring our system is prepared with the latest update before installing new services. Next, install the secure shell layer using sudo apt install OpenSSH-server-y. This dependency provides the structural framework required to establish both standard SSH and secure SFTP file transfer. To guarantee that our background service is operating properly, we check its deployment state using sudo systemctl status SSH. As shown on our screen, the daemon returned as active operation status. Then, I select file transfer permission by introducing a dedicated user account. We run sudo add user as FTP user and assign a secure password for credential authentication. Next, construct a secure directory layout using sudo mkd-p/sftp/sftp-user/upload to implement ironclad security. We assign absolute ownership of the b/sftp directory to root, read, and execute permission, while passing full ownership of the subfolder/upload over to our SFTP user. To strictly lock down our configuration, we open the SSH daemon file using sudo nano/etc/ssh/sshd_config. Inside, we open a dedicated block matching our user. We set the root directory to /sftp and enforce the internet-sftp command. This ensures that the user is safely jailed inside the home path, completely disabling the terminal shell access. To commit our security rules into active memory, we restart the service subsystem by executing sudo systemctl restart ssh. Finally, before letting client connect, validate our file system integrity using sudo sshd-t. The complete lack of output confirm that our rules are flawless and the environment contains zero structural errors. First, from the client terminal, we initiate a remote connection by targeting our server static IP gateway. We run the command sftp user alias 192.168.1.254. As expected, the system prompts us for user authentication, and upon entering the secure credential, we successfully establish a secure session as indicated by the new SFTP user. Next, we test our outbound file transfer capacity by running the command put testfile.txt. The client safely pushed the local data file up to the server. The interface displays a 100% completion transfer rate, confirming that the asset has landed securely inside the sandbox/upload directory. To verify bidirectional data flow, we then test our inbound retrieval capabilities using the command get testfile.txt. The server processes the request and transmits the file right back down to our local client workspace with zero structural error. We can easily audit the Active Directory environment during the session by executing the ls command. This instantly lists the file within the leave SFTP session, verify that our uploaded test documents are fully visible, tracked, and stored. Finally, we gracefully close our operational channel by typing exit. The connection terminates cleanly, returning our terminal back to the standard local client shell prompt with no active background hanging errors.
Now, I will explain the step-by-step configuration of the Apache web server on our Debian Linux server. The purpose of this configuration is to host a web page within our private enterprise network so that clients can access web content through a browser using the server's IP address, which is 192.168.1.254. Before installing any software, I first updated the Debian package repository using the command sudo apt update. This command synchronizes the package index files from Debian repositories and ensures that the latest package information is available before installation. Next, I installed the Apache HTTP server using sudo apt install apache2-y. This command downloads and installs Apache along with all required dependencies. Apache is the software responsible for serving web pages to users who access the server. After installation, I enabled Apache to start automatically whenever the server boots. The command used was sudo systemctl enable apache2. This ensures that the web server remains available even after system restarts. Then, I check whether Apache was running correctly by using sudo systemctl status apache2. The expected result is active running. This confirms that Apache is active and ready to accept incoming web requests. To allow users to access the web server, I configured the firewall to permit HTTP traffic. The command used was sudo ufw allow 80/TCP. Port 80 is the default port used for HTTP communication between browsers and web servers. Next, I installed the uncomplicated firewall or UFW using sudo apt update and sudo apt install ufw-y. UFW provides a simple way to manage firewall rules and control network access to the server. During the installation process, a package manager log issue occurred. To resolve this problem, I terminated the conflicting process using sudo kill-9 5419. This command forcefully stops the process that was preventing package installation from continuing. After resolving the package log issue, I completed any unfinished package configurations using sudo dpkg-configure-a. This command ensures that all interrupted packages are properly configured. Once the package issue was fixed, I reinstalled UFW to ensure the installation completed successfully. The command used was sudo apt update and sudo apt install ufw-y. This confirms that the firewall package and all required dependencies are correctly installed. After installation, I activated the firewall using sudo ufw enable. This command starts the firewall service and applies all configured rules. I then explicitly allow HTTP traffic through the firewall by running sudo ufw allow 80/TCP. This permits users on the network to access the Apache web server through port 80. To verify that the firewall rule had been applied correctly, I checked the firewall status using sudo ufw status. The output should show that port 80 is allowed. This confirms that HTTP traffic can pass through the firewall. Next, I customized the default Apache homepage. I edited the HTML file using sudo nano space/var/www/html/index.html. Then, I inserted our custom web page content. This web page serves as the home page displayed when users access the web server. After modifying the web page, I restarted Apache using sudo systemctl restart apache2. Restarting Apache reloads the configuration and applies the updated web page. I checked the Apache service again using sudo systemctl status apache2. The expected result remains active running. This confirms that Apache continues running normally after the web page modification. Next, I verified that Apache was listening on port 18. The command used was sudo ss-tulpm pipe or vertical bar grep :80. The expected output is similar to listen 0 space 511 multiply :80. This confirms that APAC is actively waiting for incoming HTTP requests on port 18. Finally, I verified the server's IP address using IP ADDR. The expected address is 192.168.1.254. This confirms that clients can access the hosted web page using the correct server IP address. In summary, the web server configuration involves 17 steps. 1. Updating system packages. 2. Installing APAC HTTP server. 3. Enabling APAC at startup. 4. Verifying APAC status. 5. Configuring firewall rules. 6. Installing UFW. 7. Resolving package log issues. 8. Reconfiguring interrupted packages. 9. Installing UFW. 10. Enabling the firewall. 11. Allowing HTTP traffic. 12. Verifying firewall status. 13. Creating a custom web page. 14. Restarting APAC. 15. Verifying APAC after configuration. 16. Checking that APAC listens on port 80. 17. Verifying the server IP address. After completing all these steps, the APAC web server was successfully deployed and ready to serve web pages to clients within their private enterprise network. After completing the APAC web server configuration, several tests were conducted to verify that the server was functioning correctly. The purpose of this test was to ensure that the Linux client could communicate with the Linux server and successfully access the hosted web page through the private enterprise network. The first test was performed to verify network connectivity between the Linux client and the Linux server. We used the following command on the client machine: ping 192.168.1.254. The expected result was 64 bytes from 192.168.1.254. The actual result showed successful replies from the server. This confirms that the Linux client can communicate with the Linux server through the internal network without any packet loss. The successful ping response verified that the network configuration was correct and that the server was reachable. After confirming network connectivity, I tested whether the APAC web server was responding to HTTP requests. I used the curl command, curl http://192.168.1.254. The expected result was that the HTML content of the hosted web page would be displayed. The actual result showed the web page content returned successfully by the server. This confirms that APAC is running correctly and can serve web content to clients over HTTP. The third test involved accessing the web server using a web browser on the Linux client. I entered the following URL into the browser: http://192.168.1.254. The expected result was that the customized web page would appear. The actual result showed the web page loading successfully in the browser. This test demonstrated that users can access the web server normally through a graphical web browser, just as they would access a website on a real network. The final test was performed to verify that the correct web page content was being displayed. I launched Firefox and accessed the web server using Firefox http://192.168.1.254. The expected output included the customized content. Welcome to Manjaro Enterprise Network Operating System mini project. Server IP address, which is 192.168.1.254, hosted using APAC HTTP server on Debian Linux. The actual result matched the configured web page content exactly. This confirms that the index.html file was configured correctly and that APAC was serving the intended web page to clients. To summarize, 4 tests were conducted to verify the functionality of the web server. First, ping test to verify network connectivity between the client and server. Second, curl test to verify that the APAC service was responding to HTTP requests. Third, browser access test to confirm that users could access the website normally. The last one, web page content verification to ensure the correct web page was displayed. All 4 tests were successful, proving that the APAC web server was properly configured and fully operational within the private enterprise network.
Step-by-step configuration and section 8.3 testing procedure for the installation and configuration of the MariaDB database server in our operating system mini project. Part 1. is installation and initial authentication. The first step is update system and install MariaDB. To begin the setup, we first update our system package repository index using the command sudo apt update. Once update, we install both the MariaDB server and client package simultaneously by executing sudo apt install MariaDB -server MariaDB -client -y to ensure all necessary dependencies were handled automatically. The second step is start and enable MariaDB. After a successful installation, we need to manage the database service. We start the MariaDB service using sudo systemctl start MariaDB and configure it to launch automatically. Furthermore, step 4 is log in into MariaDB. With the basic security hardening complete, the administrator log into the MariaDB command line interface using the root account with the command sudo mysql -u root -p to begin administrative tasks. Third step is secure installation. Security is a vital step, so we execute the security configuration utility via sudo mysql _secure installation. This allows us to improve database security by removing anonymous users and disabling insecure default setting. Step 5 is create database. Once inside the MariaDB prompt, we create a dedicated database named bakso1213/db for our project. We then run the show databases command to confirm that the database was successfully added to the server list. Step 6 is create user and grant access. Next, we create a local database user named Mandora, identified by the password. We then grant full privilege to this user over our newly created project database using the grant all privilege statement, followed by flash privilege to instantly apply the changes. Step 7 is create table and insert data. To prepare for data testing, we selected our database and create a table called staff with columns for ID, name, position, and salary. We insert 3 sample employee, records Ahmad bin Ali, Siti bin Abu, and Rajkumar, and finally, verify the table content using a standard select from staff query. Next, step 8 is allow remote access from client. Moving on to remote access, we exit the MariaDB prompt and modify the core service configuration file using the nano text editor at /etc/mariadb.conf-d/50-server.cnf. We change the bind address from the default local loop back to the server static IP 192.168.1.254 and restart the MariaDB service to apply the change. Step 9 is grant remote user access. We log back into the root database to explicitly grant remote access privilege to our Mandora user. by using the Wildcard subnet network 192.168.1%, we ensure that the user could securely connect from any client machine within that specific IP range. The final step in our configuration was adjusting the firewall to let traffic pass through. We allowed MariaDB default port 3309 TCP using sudo ufw allow 3306 TCP, reload the firewall rule, and verify the status. For testing procedure section in 8.3, for the test 1, we run sudo systemctl status MariaDB to double check that the service is still active after all the network and firewall modification. In conclusion, every single step ranging from the initial installation, database and user creation to remote access configurations and firewall adjustments was executed successfully. The server is completely operational and ready for deployment. That concludes our presentation. Thank you.
By working on DHCP, I learned that it helps automate network configuration instead of manually assigning IP address, so the server does it automatically.
Let's remind me, Albara, what is the function of DHCP?
The function of DHCP is to automatically assigning IP address and network string such as subnet mask, gateway, and DNS devices. So, mentioning of devices, what is the survive of SFTP and why is it more secure than FTP?
SFTP stands for Secure File Transfer Protocol. It is more secure because it is used as SSH encryption and protect both data and login credentials. While FTP use send data, use plain text.
This is interesting. Rasha, how did you test whether SFTP was working or not?
A Linux server SIP and successfully upload and download the file. That confirmed the server is working properly. Also verified Apache web server is running.
I use common sudo systemctl status Apache too. If it shows active running, that means Apache is running correctly.
Okay, how did you test the web server after configuration?
I tested it using curl http://192.168.1.254 and also by opening a web page through a browser. Thus, web server was working if web page loaded successfully. Elisa, what is the purpose of MariaDB?
MariaDB is an open source relational database management system used to manage, store, and retrieve data from SQL commands.
How do you test the database?
I test it by connecting to MariaDB, setting the database and tables, performing code operation, and testing remote access from that client. Before we finish, Albara, how do you know that DHCP service is running?
I check it using sudo systemctl status isc/dhcp/server. If the output shows active running, it means that DHCP is operating correctly.
All services were successfully completed and tested.
Yes, its service work properly within the private network configuration.
Overall, this project helped us to understand Linux networking, service configuration, testing, and troubleshooting.